All right. Hi, everyone, and welcome to the MAME podcast, a show where I interview interesting professors and engineers. So my name is Philip, and I'm the VP Events of the McGill Association of Mechanical Engineers, MAME. And today's guest is one of the most beloved professors at McGill University in mechanical engineering. May I introduce Professor James Forbes. Hi.
Good morning. Good morning.
So you can start by telling us a bit about yourself and, what's your connection to McGill? Like, who are you?
Yeah, sure. Okay, so yeah, my name's James Forbes. I'm an associate professor in the Department of Mechanical Engineering at McGill University. I've been here for two stints, actually. I was here from 2011 to 13, and then I've been at McGill again from 2015 to the present date, so 2020. Okay. Yeah, so that's me.
So you took a break for, was it a break from teaching or a break from?
No, I actually went and I had a faculty position at the University of Michigan for 2 years. So I was an assistant professor at the University of Michigan for 2 years. But for lots of reasons, nothing really against the University of Michigan, and just my family and we decided we wanted to live in Canada and be back in Montreal. So I came back after 2 years.
All right. And, we're an undergraduate society, so would you mind telling us a bit about your undergraduate experience?
Yeah, sure. So I did my undergraduate degree in mechanical engineering at the University of Waterloo. So Waterloo, I wouldn't say is a super well-known school, like compared to, for example, the University of Toronto or McGill. But it is well known for its undergraduate program, particularly because it has a mandatory co-op program. And when I was, 18, 19, I really liked that idea of having mandatory co-op terms. And the way it works at Waterloo is you do, what I did anyway is I did all of my first year, so the fall semester, the winter semester, and then I went right to a co-op term that summer. Second year, first semester, but then I did a co-op term right after in the winter. And then for the rest of my degree, there was a flip-flop of term at school and then term away. And so that's why I wanted to go to Waterloo, and I really liked it. It was a really good experience. I did 6 co-op terms. I worked a little bit in automotive. I worked a little bit in the rail industry. Yeah, it was a good experience.
Was your undergraduate like a breeze, or was it pretty hard?
Wow, it was definitely a shock at first. Like, I think it's a shock for everybody, right? Like, I moved away from home, and like I remember living in residence and thinking, oh man, I'm gonna do all these sports. Like I was gonna play hockey, Wednesday night, ultimate frisbee Thursday, soccer, blah blah blah. And at first I did, and let me tell you, it was a shock. Like you have to learn how to balance school. So at first, like it was brutal. Like it was really hard. But eventually, I learned to kind of get a better school extracurricular balance. And by the end of it, like you kind of get into a groove, right? So by the end of it, like you just kind of learned, or I just learned what you had to do. So no, I wouldn't say it was a breeze at all. I would say I had to work pretty hard and learn how to balance time, basically.
Yeah. Were you involved, like what extracurriculars were you doing? You mentioned sports. Were you doing like design teams or anything?
Yeah, so I always played, some sports. To this day, I still play hockey and lacrosse. For a while I did, throughout my whole undergraduate degree, I did some music, either jazz band or there was actually an orchestra. And so I played viola in this orchestra. That was actually a lot of fun. When you play music, you get exposed to a whole different, spectrum of people. And yeah, that was a lot of fun, actually. I really enjoyed that. I didn't really do design teams. For one semester, I tried to do a little Formula SAE, and I didn't design any parts for the car or anything, but I did a little bit of machining. But to be honest with you, I felt that I got some really great experience in my co-op terms, so I didn't really feel drawn to doing a design team just because I got good kind of design experience and manufacturing experience.
Yeah, exactly.
Using co-op. So yeah, I kind of always did a little bit of sports, a little bit of music. That's primarily what I did outside of school. Yeah.
So what piece of advice would you give your 20-year-old self back when you were there?
Do not have preconceived notions about anything. Like when I went into mechanical engineering, I definitely would describe myself as a nuts and bolts engineer. Like I wanted to be a nuts and bolt engineer. I really was attracted to kind of mechanisms and, um, gears and linkages, and even on some of my co-op terms, I had some great opportunities to kind of be part of a team that designed some automation equipment. And then what I learned was, for example, like heat transfer, I had this preconceived notion that like, I wasn't gonna like that, and I ended up loving it. I actually almost went into graduate studies in heat transfer because I was like, wow, that course was like awesome. And so if I could, give my 20-year-old self advice, it would be, yeah, like don't have preconceived notions about any of these courses or anything for that matter. Like I ended up really enjoying the thermal fluid side. When going into it, I thought I'd be like, no, the dynamics, mechanisms, robotics. And even though I did end up going into like robotics in the end, but I really ended up enjoying heat transfer and fluids and thermodynamics for sure.
Why did you choose to go to a master's degree instead of going into the workforce, for example?
So to be very honest, like I went to Waterloo because I wanted to do co-op because I always had this idea of just going into industry right after undergrad. But through my co-op terms, I was exposed to a lot of different kinds of engineering, like project management. And the thing is that like honestly, like when you're 20 or 21, you don't really know what engineering is because you're just going through it, right?
Mm-hmm.
And then I was very lucky to not only get exposure to kind of some manufacturing and some design and even some automation, but eventually I got exposure to actually using engineering tools like strength of materials, like stress strain calculations. I even did a little bit of dynamics calculations on one co-op term. And once I kind of realized that, like some of these more advanced courses that you don't really see how they're useful in the real world, once I kind of realized like, oh yeah, that is kind of interesting to apply that to real problems, then I decided like, I want to actually learn kind of more of those advanced tools because I wanted to be able to do some of the more advanced design stuff. And so that's what kind of motivated me to do a master's anyway. I just kind of wanted to go to graduate school, get a more advanced skill set, so that I could get a job in industry where I was doing more kind of, I'm going to call it analysis, like, using some of these more theoretical tools to kind of drive the design. That's kind of what I wanted to do. But then once I got into grad school, so here's another thing is like, I had no idea what grad school was really. Like,
Yeah.
people talk about doing research, but like until you do research, like you don't really know what it is. And then once I got into grad school and I was like, so this is what research is. Like, this is really cool. And then I decided to do a PhD after that. And then it just kind of like the ball kept rolling, right? Like I eventually said, okay, well, this research stuff's pretty fun. Like maybe I want to consider being a professor. Like when I started my PhD, I didn't think, like I didn't rule it out, but I was not set on becoming a prof.
Yeah.
But by the end of it, I was kind of like, oh yeah, this research stuff's pretty fun. And I liked the other aspects of academia, like I liked TAing, and I figured I'd like teaching. So yeah, that's kind of how that happened.
Okay, and I think you went to University of Toronto, right? You switched university for
Yeah.
your graduate. And what was your research about? Was it about pretty much the same thing you're doing right now, or similar?
So I've since evolved a little bit. Well, depending how you look at, maybe a lot since my PhD and my master's. So my master's and my PhD was on control systems, and in particular, a branch of control known as robust control. And in my master's, I looked at using numerical optimization tools to design controllers. And in my PhD, I looked at extensions of that kind of idea. Again, kind of robust control, but in a very kind of generalized way. And at the time, it was very theoretical, but kind of the toy problem I would apply my theory to would be something aerospace related, so like a large flexible space structure or a spacecraft. And then in my early years of being a professor, I still pretty much did that kind of robust control type work. And my first few PhD students, that's what they worked on. But nowadays, I wouldn't say I've done like a full pivot. Like I still do control, but now I would say I do more robotics. And what I mean by that is in robotics, there's kind of this synergy between the control, called the navigation loop, as well as the guidance loop. And also, of course, wrapped up in that is like dynamics and equations of motion related to how things move. And so now I would say that the vast majority of my students and my research projects are actually more navigation focused. And it's still coupled to control because the navigation solution then feeds right into the control solution. So we still, in my research group, we still do some control. And I would say one of the hallmarks of my research group is that like every single one of my students, when they graduate, they really understand that synergy of the estimation, the control, the guidance. So yeah, there's been a bit of a pivot since I finished my PhD, more towards navigation within robotic systems. But yeah, we still do some control. In fact, I was just talking to an industrial partner I have about future projects, and he was mentioning, yeah, there's this other control problem we have. If you have a student who's interested in doing some more rigorous control, like, let's talk about that. So yes, there's still some control involved.
All right. And I remember last year at the Professor Pub Crawl, you showed a video of, the navigation of the cart in the room. I thought it was really interesting. So you want to talk about that a bit?
Yeah, sure. So as I mentioned, a lot of my research right now is focused on navigation. Let me just give a definition of that. So given a bunch of sensor data, so say you have GPS and a rate gyroscope and an accelerometer, all these measurements you want to fuse together in an algorithm to give you an estimate of, for example, position, velocity, attitude, angular velocity. And the reason why that's challenging is because the sensors, like for example, a rate gyroscope, it's corrupted by noise. It potentially has bias. In GPS, for example, you have what are called multipath effects. And the whole idea is that you have to take all this data and get an estimate, a best estimate, an optimal estimate in some sense of where the vehicle is. So not only can you do this for cars driving on the road, you can do this for underwater robots, you can do this for unmanned aerial vehicles. And that's really where a lot of my research is now focused. I have some great partnerships with some companies. And in one of them, for example, we're doing what's called SLAM, simultaneous localization and mapping. So the idea is you don't have GPS and you have a camera or what's called LiDAR or a laser rangefinder, as well as like a rate gyro, an accelerometer, magnetometer.
Yep.
You in the SLAM solution or in the SLAM problem is you have to not only localize, so figure out where you are, but you have to map simultaneously. So that's where the term simultaneous localization and mapping comes from. And so it can be a pretty challenging problem for many of the reasons I discussed, like all the sensor noise and bias. But also what's really challenging, especially when you have a UAV, is it's highly nonlinear. UAVs, they can rotate and translate as they fly around, and that's a significant nonlinearity. And so overcoming those challenges is kind of where the research is actually. Yeah.
Sorry. And what main industry do you work with? Like you mentioned a few UAVs and cars. What's your main industry at the moment?
So that's one of the beautiful things about working in the field of robotics is these tools like control systems, navigation, they are not necessarily only for one field. And so I currently have projects with a UAV company, an underwater robotics company. I just submitted a grant proposal to work with an automotive company to do some like autonomous cars type navigation. And it's actually really, really fun. Like you can take these kind of general theories and make them specific to particular problems. And that's actually really fun. Like obviously a UAV is different than a car, and so you have to do some specialization of the algorithm or the theory to those specific situations. But what I think is really cool is this kind of bird's eye view of, you have all these tools, these numerical methods, these probabilistic tools, these control theory tools, and then it's like, oh, I'm pretty sure this like least squares algorithm will help me solve this problem. In fact, I actually have a project with some researchers at the Meekins Institute where we're looking at using control systems to help characterize the material properties of airway smooth muscle. So basically your lungs, you have lung tissue and they have certain mechanical properties. And when people have asthma, those mechanical properties change. And we're interested in using a feedback loop to help actually characterize the properties of this muscle, right? So I never thought ever I would end up doing some biomedical type engineering stuff. And that's a super cool project. Like that's been a really, well, first and foremost, it's about 1,000 times harder than I ever thought it was going to be. Before about preconceived notions.
Yeah, exactly.
Like, oh, this, no big deal. This will be pretty easy. Oh man, it's been a really interesting. So yeah, what's kind of been fun about my research over the years is I wouldn't say I've done only UAVs or only underwater nav or only aerospace. I've been able to work in a bunch of different domains. And the common thread is actually the tools, the probabilistic tools, the least squares tools, the numerical methods. Like those are all kind of the tools in my toolbox, and then I kind of apply them in these different situations.
So I've never had you as a prof, but word around is that you're one of the best profs. So what class did you teach, and what do you like? Which class do you like best?
So first of all, it's very flattering to hear that. Yeah, I'm really happy to hear that. So yeah, with regards to teaching, so I've taught. So what have I taught at McGill? So I've taught Mech 220, so Mechanics 2. I've taught Mech 309, so numerical methods. I've taught 412, so that's system dynamics and control. And then there's some graduate classes I've taught. So Mech 542, which is spacecraft dynamics, and Mech 513, which is control systems, and then Mech 642, which is advanced dynamics. Okay, so those are kind of so those courses, like there's obviously a theme there. It's kind of like the dynamics, control, numerical methods. That's kind of a generic class. To be honest with you, I have to admit, like probably my favorite course to teach is Mech 412, which is system dynamics and control. The reason I like that class like so much, actually I love that class. I love teaching that class.
I have it this winter. Are you
teaching it this winter?
Nice.
Yeah.
Sorry.
Well, that's the plan anyway,
Yeah.
For now, I'm supposed to be teaching it this winter. Yeah, the reason I love that class is because it's truly a synergetic class. Like, there's a reason why, for example, Mech 315 vibrations is a prereq. There's a reason why AEI is a prereq. Like, you really have to know, even fluids, I think fluids 1 or 2 is even a prereq. Anyway, you really have to know these fundamental things, okay? Because that course really not only builds on those fundamental things, but then combines them. And so in Mech 412, the reason I think it's so cool is it's truly a synergy of like kind of everything you've learned. Like you got to remember some of your Mech 220, you got to remember some of your Mech 315, you got to remember a little bit of your fluids, you got to remember some of your numerical methods, your ODEs, like
a combination of everything.
Yeah, it kind of brings it all together. And what I think is super cool is students realize like, oh my gosh, like all these things are connected, and in some sense they're the same. Like that's another kind of theme of the class, is in some sense they're just the same thing. Like a mass spring damper system is in some sense the same as a RLC circuit.
Wow.
And that's really cool, kind of explaining that and kind of showing that to students. And then on top of that, another reason why I love that class is that you then introduce to students this idea of feedback control, of a control system. And it's a very unique concept, and it's a very powerful concept. And it's like, it kind of comes out of left field too. Like, for example, I have a former student of mine once said to me, said, you know, you go through your degree and you take some thermo, some fluids, some heat transfer, some dynamics, some solid mechanics. And by the time you get to your, you know, your last year, you think you got mechanical engineering figured out. And then at a left field comes this thing called control systems. That's like a whole other field of engineering. And it's true. And it's a very, very powerful field. And exposing students to this idea of feedback control, and then the power of feedback control, is super, super exciting. Like, it's a very, very exciting thing to expose students to. So I really, really, really love teaching that class. It's super fun. It's not to say I don't like teaching other classes. Like, I taught Mech 309, and that was a real pleasure. Like, I'm so glad I taught that class, because it reminded me just how much I use numerical methods. Like, I was going through this book, I'm like, oh my gosh, I use this like every day. And it was a good reminder for me, even, like, oh my gosh, numerical methods is like super important. And like Mech 220, I've only taught it once, but that was a real fun course to teach too. So yeah, it's not like I don't like teaching other classes, but I'd have to say, like, yeah, I think Mech 412 is by far my favorite, just because it's so synergetic. And then on top of that, you get to teach feedback control, which is, I think, really, really fascinating field.
Yeah. So what classes are you teaching, for example, this year?
So this coming fall, I'm teaching, so there's a specialty class. It's called, it's kind of given a placeholder number. It's Mech 600, and I believe the official title is Special Topics in Mechanical Engineering. Anyway, but, the other title is Estimation and Control of Robotic Systems. That's a graduate class. It's 600 level, so undergraduates can't take it. But what that class is about is it really is supposed to expose students to the synergy between estimation and control. Not so much guidance, but estimation and control in particular applied to robotic systems. But then in the winter, I am teaching 2 classes undergrads can take. So I'm teaching 412, so Mech 412. And then I'm teaching Mech 513, which is control systems. And Mech 513 is the kind of the continuation of Mech 412. So in Mech 412, we spend, you know, we really try to emphasize, okay, you know, fluid systems, mechanical systems, electrical systems, they all are kind of related in some sense. And then you want to wrap a controller around one of those systems or many of those systems kind of working together. And it's really, 412 is really the introductory control class. And then 513 is, I don't want to use the word an advanced control class. It's just a continuation, if you will, of that introductory control. And we look at different tools, different ways of thinking of the problem. We actually use, we present this so-called optimal control framework, which is pretty interesting. In 412, there's always this question of, like, well, how do we kind of come up with the control parameters? And I'll be honest, like, basically when we, you know, I teach it, I say, well, you tune it. But then in Mech 513, we can actually pose these so-called optimal control problems where you can find optimal controllers. So that's kind of the extension. So that's yeah, I really enjoy that class too. That's a super fun class to teach.
Yeah. So, oh, cool. Now, on a different note, how have you been adapting to the COVID situation with your teaching?
It's been, yeah, it's been rough. So I have 2 little kids. They're 6 and 3.5. And so, like right now, my wife's taking them both to the park. In the house, they'd probably be walking in like right now, which is happening. Like, I've been on Zoom meetings and my kids just walk in. You know. So yeah, it's been challenging. Honestly, some days are just jam-packed Zoom meetings, like just a domino of Zoom meetings one after the other with industry partners or students. And other days I try to just block off like a whole morning so I can kind of do other quote unquote chores. Like I gotta write reference letters. I gotta do
interviews with young undergraduates.
yeah, stuff like that. Or actually I have to write a reference letter. That's on my list of things to do this morning, is write a reference letter for someone for graduate school. Or I try to block a whole morning off to do actually some research, like actually kind of get into the weeds of the math and write some code. So at first it was pretty rough, the first couple of weeks, but then my family and I, we got into kind of a pretty decent groove where I'm able to pretty much work solid from 9 till noon. And then I help out with doing lunch. And then in the afternoon, I can usually get another hour or two of work done. But by 3 o'clock, like I gotta go help. It's yeah, so it's but I think the thing that we all gotta realize is yeah, we all kind of gotta manage expectations, right? Like, you know, we can't be I'm absolutely not working at 100%, you know, like I'm probably 80% capacity or whatever. And I think when it comes to teaching in the fall, like I think we all got to be reasonable, like just have reasonable expectations of each other. Like, so that's kind of my outlook, if you will. It's been tough, but it hasn't been like
right.
I've still been able to get stuff done.
Do you think it's gonna change how universities operate?
I honestly don't know. I myself have been pleasantly surprised that, you know, even though I'm not working at 100%, you know, I've been pleasantly surprised I'm still able to work at probably 80%. I've been pleasantly surprised that, you know, interacting with my graduate students has been actually fine. And yeah, shout out to my grad students. Like they are still like killing it. They're doing awesome. So I think we are going to be in the future probably more open to using, for example, Zoom as a communication platform. Or yeah, where I could see a change, to be honest, is videos, pre-recorded videos. I could definitely, because you know, it's always a barrier to entry. Like, you know, professors, like we're busy. You know, it's like students are busy, right? Like we're all busy, and the activation energy to learn how to put together an online lecture, just the effort, you know, was a deterrent basically. But now that we're all kind of forced to do this, like I think professors are going to be like, oh, well, yeah, why don't I put a couple tutorial questions online? Why don't I do like this one lesson online? And then, so yeah, I think we will see some change, but I'm hesitant to say like, oh yeah, for sure, this is going to change education.
Yeah, for sure.
I think there'll be some change, but I don't know what's going to really happen.
And you mentioned you work with, do you work with a lot of graduate students, or like how many do you have per year or per semester?
Yep. So right now I have 2 SURE students, so undergraduate summer students, who are really great. They're really doing really well. They're awesome. And last count, I think I had, I don't know, around 10, 11 graduate students, so master's, PhD students. I have 1 research assistant. So the group all total is around 14 or 15. So yeah, that's a lot. It's yeah, it's a struggle to keep up with them sometimes. But luckily they're, you know, unbelievably talented young men and women, and they are really good with keeping on task. And when we do our weekly meetings or our bi-weekly meetings, half the time they're just updating me on the awesome stuff they got done. And sure, they get stuck, like everyone gets stuck, and so I help get them unstuck and on to the next problem. But yeah, they've been doing really well. They've been doing great.
Yeah, cool. And you work with you said 2 SURE students. That's kind of you know, a lot of, for those who don't know, SURE is the Summer Undergraduate Research in Engineering. So you get to work with a prof for the whole summer, and do you work with students every summer?
Yep, I make an effort. I make an effort to have around 2 usually. I've had 4 in the past. I've had actually I've had one summer I think I had none, but I definitely make an effort to have 2 um, because like they generally are able to get decent work done. And also it's an investment. A lot of these students end up doing their masters with me, and it's a great way. It's like a win-win for everybody. The student kind of gets to interview me in some sense, that they can see what it's like working with me, and they can figure out how demanding and crazy I am. And at the same time, I get to kind of interview them. It's like a 4-month interview, right? And it's actually basically the same thing that I did as a co-op student when I was an undergrad.
Right.
Like a lot of companies I worked for, they really treat the co-op process as a way to get a 4-month interview out of somebody. And so, yeah, I definitely think it's worthwhile to have SURE students in my lab. Actually, just today, both SURE students are, there's a whole process, and rightly so. There's definitely, because of COVID, there's a very structured process to go in the lab. So we're following that process very rigorously. And yeah, they're in the lab today collecting data. I'm pretty sure if all things go well, they'll end up actually publishing a conference paper out of their SURE project. So yeah, it can be very, very fruitful for everybody, for me, for them.
And they also work in navigation, or what topic do they?
Yep.
Yeah.
So the one student, she's doing, very much a navigation focused project. The idea is when you have a UAV or a car, and say you had actually 2 GPS receivers, or there's this other localization technology called UWB, ultra wide bandwidth transceivers. And so the idea is if you have 2 of them on a vehicle, what kind of properties does that have? How can you enhance the position and attitude estimate even more? And she's done some really great preliminary work, and now we're collecting data for her project. And yeah, I'm pretty confident that we'll get a conference paper out of that, which will be really great. And actually just recently, just yesterday, I actually talked to an industrial, like a company, and they mentioned they actually do put 2 GPS receivers on their vehicle. And I was like, oh yeah, well, I'm actually doing something similar with a slightly different twist. And they basically said, oh man, we need to talk. Like that sounds, yeah, we should definitely touch base on that once you have the results. So that might lead into a cool project with them. And the other student is, okay, so nowadays, especially because I'm in robotics, you cannot, put your head in the sand and deny that machine learning AI is not a thing. Like everybody and their kid brother, kid sister is working on some sort of machine learning or AI or something like this. And so I'll be honest with you, I was a little skeptical of this whole ML AI kind of wave. And the reason is because I'm very much of the opinion, you want to use the right tool for the right job. You don't want to use a hammer when you need a screwdriver. And I just kind of found, I'm like, wow, like there's, why are people applying these ML AI tools to certain problems when there's very good tools that can solve that problem? I didn't kind of see that I didn't agree with that point of view. But after a while, I, dug into the kind of the ML AI literature, and I realized, oh, well, this is, just another tool, right? Going back to what's the word? Misconceptions or pre-notions. But once I kind of like dug into it, I realized, oh yeah, this is just another tool. And I kind of realized, oh yeah, there's definitely some problems where this is definitely applicable. So that other SURE student, he's doing whole hog machine learning, but we're applying it to navigation. So we're actually using some UWB data to solve the localization problem quite differently, using some ML tools, machine learning tools. And so far, the results are promising. I wouldn't at all say we've kind of like figured it all out, but we have some results that look promising. and that might dovetail into some other projects down the line. So that's pretty exciting.
And how do you choose your sure students? Do you only choose people you know, or like fourth year that know everything?
Because my research and just the fields of navigation, guidance, and control are pretty mathematically sophisticated. Like you really need to know math. Like you need like linear algebra, ODEs, and you really need to know that. It's really hard to take on students who haven't taken, for example, at least Mech 309, for example.
Right.
So I don't want to, dishearten anyone and say, oh, I'll never take on a more junior student, but I also just want to be honest that, to do this robotics stuff, you kind of need to know
Advanced.
math. Because the other thing to realize is like in my group, we're not actually building the robot, right? Like we're not like
Yeah.
up some robot and like laser cutting and machining stuff. Like we're really on the algorithm side. And so what does that mean? Like it literally means doing the math to like derive an algorithm and then implementing that algorithm in code on either just on your, like you either collect the data and just run the code on your laptop, or you actually implement it on the robot. And so like if I had projects that were, maybe more hands-on, I would take some more junior students, but just the nature of what we're doing involves like, well, let's actually derive an algorithm, code it up, collect data, test it out.
Yeah, a lot of people, when you don't know robotics, you think about like building the machine, but there's actually like the big part of navigation, controls, and programming. So it's been great talking to you, Professor. Now, what's next for you? Do you have any plans or ambitions or dreams for next years?
Wow, that's a loaded question. Yeah, I think so. I guess my immediate goal is to start. Not that I haven't been trying to have big impact, but to keep on trying to develop new theories and algorithms that are going to be quote unquote big impact. So what does that mean? That essentially means displacing a whole other way of doing something. Because my collaborators and I come up with a better algorithm. Yeah, I think that's kind of the end goal, is to really look for or try and develop a game-changing way of doing things on either the navigation or the control side. So that's what I hope to do in the future. I also hope to still keep on working with industry. Yeah, working with industry is great for lots of reasons. You get so one reason is you get exposure to problems you didn't even think were problems, right?
Right.
And it's on one hand, don't get me wrong. Like on one hand, I kind of like the idea of just kind of doing theory for theory's sake. But on the other hand, I definitely like the idea of solving like a real problem. And sometimes to solve that, real world problem, you don't need sophisticated theory, and that's totally fine. And other times to solve that real world problem, like you have to literally invent new theory, which is really fun. So in the future, as I try and, have a big impact, I still want to have an impact with industry and work with industry. By the way, the other reason I like working in the industry is it's a really good way to recruit excellent graduate students. A lot of students, when they finish undergrad going to graduate school, and I don't, not a slight on anyone, but they don't really know the power of theory yet, I would say. Like they've kind of seen theory, but they haven't really kind of, I would say, learned to appreciate the power of it. So if I go pitch a project that's like just some applied math project, like students generally don't bite at those. The other reason why working with industry is really great is because then I can kind of pitch, okay, look, there's this company that's got this problem and we need to do some theory to solve it. And usually in their minds, I think, speculate anyway, they're like, oh, sweet, an applied problem.
Yeah.
Months into their degree, they realize like, oh man, this theory stuff, like we'd be sunk without it. Eventually kind of bring them to the dark side, if you will, appreciating all this math. That's the other reason why I want to keep on working with industry, is because it's actually a great recruitment mechanism. And in Canada, we're super lucky to have really great matching programs, I would call them. There's this thing called MyTax, or there's an NSERC Alliance grants where the company puts in $1, the government will match, and then those $2 can go to the graduate student or the project in general. And so there's good incentives for companies to collaborate with academics. So yeah, I still want to do that. Yeah, I think just in general though, I just want to keep on having or trying to have an impact, both from the point of view of the field as a whole, but as well as helping companies in the local Montreal ecosystem.
Great. Well, thank you for taking the time to interview, to let me interview you. I know a lot of people will find value in what you're saying. So I thank you, and I hope to see you in 412.
Yeah.
And, you have a lot of pressure to be a great prof, as I've heard from everyone.
Well, I'll do my best. I'll do my best.
All right. Bye.
All right. Thanks so much.